So one more concept related to our series RLC circuit. So we have an alternating source, we have a resistor, we have an inductor, we have a capacitor connected in series. We know the source voltage is alternating with time, which in turn causes the current that's flowing in the circuit to also alternate with time. In terms of figuring out the peak or maximum amount of current that can flow in our circuit, that is directly related to the source voltage and inversely related to this impedance. So Z is kind of the overall ohms of the circuit. Well, it is the overall ohms of the circuit. It's kind of like an equivalent resistance of sorts. Z depends upon R, the actual resistor value, and then it also depends upon the XL, which we call the inductive reactance, and XC, which we call the capacitive reactance. XL depends on the frequency, specifically the angular frequency that the source is oscillating at, and the inductance. Capacitance depends upon the angular frequency of the source and the capacitance. So both XL and XC will change if we change the oscillation frequency of the source. Okay, concept of resonance. We briefly mentioned resonance when we were talking about oscillations. So for example, you push on a kid on a swing. You have this child, oh, didn't mean to make everything move. But if you push the kid on the swing, if you want to get the child swinging higher and higher and higher, which is typically what the child wants to do, you need to apply a force on the child every time they start swinging away from you. So you match the frequency, you apply the force to the natural frequency of the swing, the child on the swing. By natural, just this frequency the child is swinging at, even if you're not pushing. If you match the frequency you apply your force to this natural frequency of the swing, the child swings higher and higher. Meaning the amplitude increases. The amplitude of the motion specifically. This example of forcing a system to oscillate at this natural frequency where we get a larger amplitude is called resonance. In a circuit, when we talk about amplitude getting bigger, we're talking the amount of current. We know the amount of current in a circuit, in specifically this series RLC circuit. The current depends on the source voltage and it depends upon Z, but that means it depends upon the angular frequency. So the natural frequency of an RLC circuit, it's also called a resonant frequency, occurs or is determined by the smallest possible value of Z. So that current I is biggest when Z is smallest. Well, if we look at this equation for Z, we always have the R squared, so the resistance, plus some quantity of XL minus XC squared. So we're always adding this quantity. Ultimately, this natural frequency will occur if XL is equal to XC. Because if XL and XC are equal, this second term goes to 0, meaning we're not adding anything to R, and Z will equal just R. Now, that doesn't mean there is no capacitor or no inductor. We just mean that their reactances are equal. Now, XL we know is omega L. XC is 1 over omega C. So if I get the omegas to the same side and solve, we find that omega is the square root of 1 over LC, which of course we could also write as 1 over the square root of LC. This is called the resonant or natural angular frequency, because it is in radians per second of our circuit. You've seen this equation before when we talked about those ideal LC circuits. This was the angular frequency we came up with, the oscillation rate of the energy between the inductor and capacitor. So in an AC circuit, this same angular frequency is a situation of resonance, meaning we're going to get the largest possible amount of, or peak value of current flowing. If our angular frequency of the source changes at all, that will change Z and will make Z larger, because if we change the frequency, XL minus XC will no longer be 0. And if XL minus XC is not 0, then Z is bigger than R. If Z gets bigger, then that peak value of current gets smaller. So in resonance, we are maximizing the peak or maximum value of current. We're getting the most or largest possible peak value of current. Another way we can look at that, we're maximizing the power output. Power we can write as the 1/2 IRMS source voltage RMS times the cosine of phi. That power factor, cosine of phi, is equal to R over Z. In this specific example of resonance, where R and Z are the same value, cosine of phi is 1. This cosine of phi term were the largest value it can be. And thus, the power is the largest it can be as well. And so the power is going into creating the light or the heat or whatever this circuit is supposed to do. In a circuit where you have an RLC circuit that's receiving a signal, like your radio, a radio in a car, when you set the radio station, if you set the radio station at some sort of hertz, some number of hertz, that means you're making omega equal to the square root, 1 over the square root of LC. this radio station that you are receiving and wanting to listen to, if it matches the resonant frequency of your circuit, it will cause the largest amount of current flow, which in turn is what your radio circuitry picks up and you listen to. So we can directly relate that frequency to omega. Omega, it's just a unit conversion. Omega is in radians per second, frequencies in hertz. So to convert to radians per second, we need the 2 pi. So in your radio station, if you change the station and you want to listen to a different station, you're changing either L or C. It depends upon how the circuit is constructed. So you have either a variable inductor. An example of something like that would be a coil, and then some sort of ferromagnetic material that you can slide into the core here. When you have a ferromagnetic material and you slide it in, that changes the inductance. So the same coil with this core has a different inductance. And that core can go partway in or all the way into the coil. But by moving that core, that's changing the inductance. You could potentially have a variable capacitor. That would most likely be plates where one of the plates can be moved back and forth and different amounts of area, different areas overlap. When we talk about capacitance being directly related to area, if the area we care about is only the overlapping area. So we could have the one plate here and the other one just overlap halfway, or both plates overlap perfectly. That would be different capacitance. If the plates overlap perfectly, we have more capacitance. So we're talking resonance whenever we have a circuit of some sort that is receiving a frequency, an electromagnetic wave by way of an antenna. Now, to kind of show you this, I found a video clip. Love YouTube, you know. There's no talking in this video clip, but they do have an inductor and capacitors set up and hooked up to a light bulb, which would be resistors, a resistor, and they vary the inductance and they vary the capacitance. What I want you to look at is the brightness of that light bulb. Remember, brightness is directly related to how much current is flowing through the light bulb. So if there's more current, then the light bulb will be brighter. And so they just go through a variation of changing capacitance and changing inductance. So by moving that core, that distance gave it a XL equals XC, but now changing capacitance, the light bulb gets dimmer. So they're just showing a variation of changing inductance versus changing capacitance. Whenever Notice he always stops when the light bulb gets brightest, because if it's brightest, then we've achieved resonance. But if he changes C or L, that changes the resonance frequency and has to change the other to get back to the brightest light bulb. So resonance, that's what we're talking about. Brightest light bulb, because we have the biggest amount of peak current, which means the biggest RMS current, which means the brightest, the biggest power for that resistor. So resonance is just making Z as small as possible such that the current is as big as possible.